Dear children, today we are going to discuss the halogen compounds. Myself, Dr. Digna Varghese. Halogen compounds. Compounds obtained by the substitution of one or more hydrogen atoms of hydrocarbons by halogen, that is fluorine, chlorine, bromine, or iodine. Atoms are called halogen derivatives of hydrocarbons. Examples: alkyl halides, aryl halides, etc. Here you can see the replacement of a hydrogen atom of an alkane by a halogen gives an alkyl halide. Here you can see a methane molecule, that is a hydrocarbon in which carbon atom attached to four hydrogen atoms in a tetrahedral fashion and forming methane molecule. One of the hydrogen atoms of methane replaced by a halogen gives, here the chlorine atoms replaced one of the hydrogen atoms of methane molecule and form an alkyl halide. Here it is methyl chloride forms from methane by the replacement of hydrogen atom by chlorine atom. So alkyl halides may be classified as three types. One is primary alkyl halide, another one is secondary alkyl halide, and the third one is tertiary alkyl halide. Primary alkyl halides. The halogen atom attached to the primary carbon atom. Illustration of the primary alkyl halides are given here. Here you can see CH3, CH2, 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 Cl. The halogen atom attached to the primary carbon atom. So it is the primary alkyl halide. It is the N-butyl chloride or 1-chlorobutane. Another example is CH3, CH, CH3, CH2, Cl. Here the chlorine atom attached to the primary carbon atom. This compound is isobutyl chloride, or you can name it as 1-chloro-2-methyl propane. So the halogen atom attached to the primary carbon atom, that is known as primary alkyl halide. Secondary alkyl halide. Here the halogen atom attached to the secondary carbon atom. Such alkyl halides are known as secondary alkyl halides. Here you can see an example: CH3CHCl, CH2CH3. The chlorine atom attached to the secondary carbon atom, so it is known as secondary alkyl halide. The compound is secondary butyl chloride and it is also named as 2-chlorobutane. Chlorine atom is attached to the second carbon atom. Tertiary alkyl halide. The halogen atom attached to the tertiary carbon atom. Here you can see tertiary butyl chloride, that is 2-chloro-2-methyl propane. The chlorine atom attached to the tertiary carbon atom. Preparation of alkyl halide. The alkyl halides can be prepared from alkanes by halogenation under suitable conditions. The reaction is an example for radical halogenation because it involves free radical mechanism. Halogenation of alkanes involves the replacement of one or more hydrogen atoms of the alkane molecule with a corresponding number of halogen atoms. Here you can see the halogen atom reacts with alkane molecule and forming alkyl halide. The alkane in which hydrogen atoms are there, the number of hydrogen atoms of the alkane molecules replaced by the halogen atoms that will show or the molecule, the alkyl halide molecule with a corresponding number of halogen atoms. The reaction conditions is that this reaction takes place in two ways. First one is the photochemical ways, that means the presence of UV light. Another method is thermal method, that is the reaction halogen atom plus alkane undergo at high temperature in the range 250 to 400 degrees Celsius and forming alkyl halide. The order of reactivity of the halogen atom is that fluorine greater than chlorine greater than bromine greater than iodine. The most reactive halogen, that is fluorine, reacts too explosively, and iodine, that is the least reactive halogen, reacts too slowly and reversibly with alkanes, and hence these reactions are not much practical interest. So only chlorination or bromination is considered here. So now we are going to discuss the chlorination. Alkanes react with chlorine either in the presence of UV light or upon heating at 250 to 400 degrees Celsius to yield their chloro derivatives. Here you can see the methane molecule that reacts with chlorine in the presence of light or at 250 degrees Celsius. It forms methyl chloride plus hydrogen chloride. Another example is ethane reacts with chlorine in the presence of light or at 250 degrees Celsius, giving ethyl chloride plus HCl. The extent of chlorination depends upon the amount of chlorine used and also upon the individual alkane molecule. Here you can see one chlorine is replaced one hydrogen atom. So it forms methyl chloride. Here in the case of ethane, only one chlorine atom replacing one hydrogen atom and forming ethyl chloride or chloroethane. If sufficient chlorine is used, the monochloro derivatives undergo further chlorination reaction with successive replacement of the hydrogen atom by chlorine atoms. Here you can see a sufficient number of chlorine is used. The monochloro derivatives can be further undergo chlorination reactions with the successive replacement of chlorine of the hydrogen atoms by chlorine atoms. You can see here methane reacts with chlorine in the presence of light or temperature, giving methyl chloride. If sufficient amount of chlorine is there, the mono derivatives of the methyl chloride undergo further chlorination reaction by the replacement of hydrogen atoms and forming dichloromethane. So methyl chloride reacts with chlorine, the same reaction conditions forming dichloromethane. sufficient amount of chlorine is also there, it will undergo further chlorination reaction and forming trichloromethane. That is, dichloromethane reacts with chlorine in the presence of UV light or to 50 degrees Celsius, forming trichloromethane plus hydrochloric acid. Trichloromethane is also known as chloroform. And here you can see the CHCl3, that is trichloromethane, reacts with chlorine, the same reaction conditions, giving CCl4, that is carbon tetrachloride plus HCl, that is tetrachloromethane forming. So here you can see the CH4, here 4 hydrogen atoms are here that reacts with chlorine to give the 4 chlorine atoms substituted compound, that is tetrachloromethane. So chlorination of methane molecules gives a mixture of products, that is methyl chloride, dichloromethane, trichloromethane and tetrachloromethane. In the chlorination of higher alkanes, from propane onwards, isomeric products will be obtained. Here you can see propane reacts with chlorine either in the presence of light or by heat. You can see isomeric products, that is 1 chloropropane or 2 chloropropane is obtained. Here 1 chloropropane the yield is 45% and 2 chloropropane the yield is 55%. In the case of butane, reacts with chlorine in the presence of light or heat. You can see the isomeric products, that is 1 chlorobutane or 2 chlorobutane. Here the 1 chlorobutane is the major product. So in the case of higher alkanes that reacts with halogen atoms forming isomeric products. The extent to which each isomeric product is formed depends on the relative rates of formation of the product and also depends upon the several factors such as the relative stability of the compound or the intermediate free radicals formed or the step of mechanism that will give the yield of each isomeric product. Bromination. Bromine reacts with alkanes either in the presence of UV light or at 250 to 400 degrees Celsius to yield the bromo derivatives of alkanes. The reaction is similar to chlorination. Here you can see methane molecule reacts with bromine. You will get methyl bromide plus hydrogen bromide. Methyl bromide is also known as bromomethane. Another example is ethane molecule reacts with bromine in the presence of light or at 250 degrees Celsius, giving bromoethane plus hydrogen bromide. Now we are going to discuss the preparation of alkyl halides from alkenes. Here you can see the simplest alkene ethene reacts with a halogen acid like hydrobromic acid to form ethyl bromide or bromoethane. Here the each side of the double bond is same, or that means it is a symmetrical alkene. So it reacts with any halogen acid and form the hydrogen added to any one of these two carbon atoms, or bromine can also add to any one of these carbon atoms and forming bromoethane. Another example is 2-butene that reacts with hydroiodic acid. Here you can see the hydrogen atom can add to any carbon atom, or iodine can add to any carbon atom here because these alkenes are symmetrical. So the hydrogen iodic acid reacts with butene to form 2-iodobutane. But the compound alkene is, if it is unsymmetrical, it will add to, or the hydrohalogen acids add to the alkene, unsymmetrical alkene, in accordance with the Markovnikov's rule. That you can see here, it is an unsymmetrical alkene, that is 1-propene. The hydrochloric acid is added to in such a way that the hydrogen atom attached to that carbon atom which contains greater number of hydrogen atoms, and the chlorine atoms, that is the negative part of the molecule here, attached to that carbon atom which contain lesser number of hydrogen atoms. Okay, so this addition of halogen acids to symmetrical alkenes or unsymmetrical alkenes, it is different. If it is an unsymmetrical alkene, it will follow the Markovnikov's rule. Markovnikov's rule, proposed by Markovnikov, a Russian chemist. The addition of hydrogen halide acid to an unsymmetrical alkenes takes place in accordance with Markovnikov's rule. Markovnikov's rule states that in an ionic addition of an unsymmetrical reagent to an unsymmetrical alkene, the positive part of the adding molecule goes to the carbon atom which bears the greater number of hydrogen atoms. Okay, here you can see the propene reacts with hydrochloric acid. The positive part is hydrogen here, that will go to the carbon which contain more number of hydrogen atoms. So it will go to CH2 carbon atom and forming CH3 here. The negative side of the molecule, that is chloride ion, which will attach to that carbon atom which contain lesser number of hydrogen atoms. Here you can see the chlorine atom attached to the CH carbon atom. So this type of addition takes place in accordance with the Markovnikov's rule. The addition of HBr or HCl or HI to an unsymmetrical alkene in the presence of a peroxide apparently occurs contrary to the Markovnikov's rule. This is known as anti-Markovnikov's addition, which is known as peroxide effect or Karash effect, because this is first proposed by in 1933 M.S. Karash. Here you can see a propene reacts with hydrobromic acid in the presence of benzoyl peroxide to form N bromopropane, that means the bromide ion attached to the carbon atom containing more number of hydrogen atoms. This is contrary to the Markovnikov's addition. In the case of Markovnikov's addition, the bromide will undergo reaction with this carbon atom. But here, in the presence of peroxide effect, the negative part of the molecule attached to the carbon atom that contain more number of hydrogen atoms. Such effect is known as peroxide effect. It is also known as crush effect. This only happens in the presence of peroxide. Thank you for your attention.